Good morning, everyone. This is group number 53, and now it's our presentation. There are 4 members in our group, and you can see their names here. Our project topic is block cipher and lightweight block cipher. This presentation is simply divided into 4 parts: background, introduction, design, and conclusion. Now let's start from background part. Block cipher is a common term in cryptography. From the lecture, we know that encryption can be divided into 2 parts: asymmetric key encryption and symmetric key encryption. For symmetric key encryption, it contains block cipher and stream cipher. Our project just focuses on block cipher. For block cipher, we know that AES, Advanced Encryption Standard, is the most common encryption, which can be used in many places such as iMac, Apple Watch, and Google Home. However, for some resource-restricted environment, like sensor network or radio frequency identification environment, where there may be limited computing power, space, or memory, lightweight block cipher starts to make a difference. Now, let my teammates introduce some common lightweight block ciphers.
The first lightweight block cipher we're gonna introduce here is the Hyde block cipher, which is proposed by Hong in 2006. This is a Feistel-like cipher with 64-bit block length and 128-bit key length. And the operation of its algorithm are simple, which are only XORs, addition mode of 2 to the power of 8, and left bitwise rotation. So it is hardware-oriented rather than software-oriented. This graph here shows its basic principle. We can say it consists of 4 components. Firstly, the plain text is sent to the initial transfer function. Here, the WK is called whitening key generated from the key schedule. Then the intermediate value is passed to a 32-round function with the subkey SK from the key schedule. Finally, the final transfer function will product the cipher text with other whitening keys. The author implemented the Hyde block cipher and compared it with the AES cipher. Obviously here, by using similar numbers of logic gates, the throughput of the Hyde is far more than AES. Besides that, Hyde is simpler circuit. Since it is a Feistel-like cipher, its encryption process can be simply converted into its decryption process. So that it does not require much more cost than the encryption-only circuit. And its every operation is 8-bit process-oriented, so it performs better than the simple environment. It also combines XORs and addition mode of the 2 to the power of 8, so it has more resistance against the existing attacks. Finally, the master key value runs the whole algorithm, so there needs only one 128-bit register for it.
Now let me introduce a new ultralight block cipher, Light Encryption Device, LED. It is designed to achieve small hardware footprint while keeping reasonable software performance. LED uses SPN structure, and it is an AES-like cipher. The block size is 64 bits, and the key supports from 64 up to 128 bits. The figure shows the pseudocode of the LED cipher. It performs 2 operations. One is add round key, and the other is step. Add round key combines nibbles of subkey with the state, respecting array position using bitewise XOR. Step is a sequence of 4 identical rounds. The number of steps during encryption depends on the key size. For 64-bit key, there are 8 steps, so the total rounds are 32. For bigger key size up to 128 bits, there are 48 rounds. In each round of the step, there are 4 operations and constants, which applies round-dependent constants to each cell of the 2 first columns. Subcells, this operation applies present S box to every nibble. Shift rules. which makes every cell in row I rotate I position to the left, and mixed chrome serial, which applies a transformation in each chrome of the state by multiply by the MDS matrix. Compared with conventional cipher, LED uses a very simple key schedule, and the round key is the initial key, which improves the encryption speed and reduces the hardware implementation scale while retaining the software performance of the implementation. Among all lightweight cipher, LED has least number of gate equivalents.
Simon and Spark block cipher, which were both designed in July 2013 by NSA. The aim to design these two similar ciphers is to meet the secure and flexible need for many small devices. Simon and Spark need to be used for certain size of message. The table in the left side is the size of the block message and the corresponding key. In Simon and Spark algorithm, there are three kinds of keys, which is expressed by M words key. The M need to be 2, 3, or 4. Sometimes, for the same block size, it may have different kinds of key. For different size, Simon and Spark need different rows. The rows function is shown in the right side. In the picture, SI denotes the left circular shift by I bits, and X denotes the subcipher after I steps of encryption. In this table, it shows the performance of Simon and Spark and other block cipher in hardware and software for the block size of 48 bits and 64 bits. It is easy to see that both two ciphers perform good in hardware and software. For the same throughput, the area needed for the two ciphers and the flash are less than other ciphers. Also, we can see Simon had a better performance in hardware, while Spark did better in software.
When designing a lightweight block cipher, we need to consider a lot of things. First, basic measurement unit. Gate equivalent is an essential value of measuring the cipher is light or not. GE value can be treated as the complexity of encryption algorithm. For example, for lightweight block cipher present, its GE value is 1570, while for low-cost implementation of AES, it's 3600. Then, throughput. Throughput is also a vital value for measuring the performance of ciphers. The metric is normally defined as output bits per second. The last one is balanced efficiency. It is the ratio of throughput to area, which is seen as GE value when using same technology. The higher it is, the better cipher is. It combines the first and second metrics and makes it obvious to evaluate performance. For basic requirements, lightweight block cipher should take security, low cost, and performance into consideration. Although we need to put this kind of algorithm into restricted environment, over pursuing low cost or low space may lead to failure of encryption. Take DST as an example. It would be simply cracked by brute force attack because of its oversimplified key size. In conclusion, in this presentation, we introduce several lightweight block ciphers and make a simple comparison between normal and lightweight block cipher. At last, we present the difficulty of finding the trade-off points through an example, saying that excessively chasing one trait is not advisable. Thanks for listening.